The mysterious force of gravity, a universal puzzle. In the vast emptiness of space, where the silence is absolute and the void seems infinite, there exists a force so powerful it shapes the very fabric of the cosmos. It pulls, it stretches, it binds entire galaxies together. Yet it does all of this with no visible medium, no apparent conduit through which it can travel. This force, known as gravity, is one of the most fundamental and mysterious forces in nature. It governs the motion of everything from the smallest specks of dust to the largest clusters of galaxies, yet remains one of the greatest unsolved puzzles in science. As we look out into the universe, we see the unmistakable evidence of gravity's dominance. Galaxies spiral majestically, held in orbit by the invisible force. Planets circle stars in perfect harmony, their paths defined by gravitational pull. Stars, having completed their long life cycles, collapse under their own weight, giving birth to black holes, regions of space where gravity's power becomes so intense that not even light can escape. But the question that remains, the question that has captivated minds for centuries, is how does gravity work? How can a force so powerful stretch across the vast emptiness of space, affecting bodies millions or even billions of light years away without any apparent medium to transmit it? To explore this mystery, let's begin with a simple yet profound observation. Every object with mass exerts a gravitational pull. It's not just the Earth pulling on us or the Sun pulling on. The planets, every single object in the universe, from the smallest asteroid to the largest galaxy, exerts some gravitational force. This was first discovered by Sir Isaac Newton in the 17th century when he formulated the law of universal gravitation. Newton proposed that the force of gravity between two objects is proportional to their masses and inversely proportional to the square of the distance between them. This elegant equation seemed to explain much of the motion we observe in the cosmos. But there was a problem. Newton, despite his genius, did not have an answer to the deeper question: how does gravity travel? What medium does gravity use to exert its influence across the vast stretches of space? In the 17th and 18th centuries, people assumed that all forces required some sort of substance to transfer them a material medium. The idea of gravity acting without any visible means of transmission seemed paradoxical. Could gravity be a force that acts across empty space without anything carrying it? The breakthrough came centuries later with Albert Einstein's theory of general relativity, which revolutionized our understanding of gravity. In this new framework, gravity was not simply a force between objects, as Newton had proposed, but a warping of space and time itself. Einstein's concept of space-time suggested that massive objects like stars and planets bend the fabric of the universe around them, creating what we now refer to as a gravity well. Rather than thinking of gravity as a force transmitted through space, Einstein showed that gravity is an effect of the curvature of space-time. When an object with mass is placed in this curved space-time, it follows the paths determined by the warping which we experience as the force of gravity. This realization raised an even deeper question: how can space-time be warped? And how can the force of gravity reach across the void if there is nothing in the space between? Einstein's theory suggests that this warping, and by extension the force of gravity, does not need a material medium to propagate. Space-time itself, the very fabric of the universe, is enough. But the mystery doesn't end there. For one thing, the speed at which gravity travels is still something we are trying to measure. Einstein proposed that gravity, like light, would travel at the speed of light, a concept that was confirmed experimentally with the detection of gravitational waves, which move at the speed of light. However, how these waves propagate through space-time and how they interact with the objects they encounter remains an enigma. To understand this more deeply, imagine a massive object, such as a star or a planet, sitting in the vast emptiness of space. This object, through its sheer mass, distorts the space-time fabric around it, creating a gravity well. Objects around it, including smaller planets or even light, are affected by this curvature, their paths bending in accordance with the curvature of space-time. But here's the paradox. The gravity well, despite being a real and powerful effect, is invisible. It has no substance, no material form. It exists only as a warping of space-time, and yet this unseen warping is powerful enough to control the movement of entire galaxies. How can something so intangible have such a profound influence? This mystery is at the heart of what makes gravity such a captivating puzzle. In the vast emptiness of space, far from any stars or planets, gravity still exists. It reaches across the cosmic void, influencing objects billions of light years away. The force is felt even in the most remote corners of the universe, pulling on objects, bending light, curving the very space in which everything resides. The cosmic bodies we see moving through space, stars, planets, galaxies, are all influenced by this unseen force, as though caught in an invisible web woven throughout the universe. But how does this web stretch across the void, with no apparent medium through which to travel? And how does gravity act at all in a vacuum where we assume there is nothing to carry it? Perhaps one of the most profound aspects of this paradox is the way in which gravity seems to defy our intuitive understanding. We are used to thinking of forces as being transmitted through some kind of substance. We push against air to move or stretch a rope to apply tension. But gravity, unlike any other force, is not carried by particles or waves in a traditional sense. It acts through space itself, bending the very structure of reality. In this way, gravity is not like other forces we encounter in our daily lives. It is a cosmic force, shaping the universe not through contact or substance, but through the very fabric of existence. And then there is the issue of gravity's reach. If we stand on Earth, we feel its pull. We know that gravity is responsible for our weight, for the falling of apples, and the orbits of the planets. But when we look up at the stars, when we observe galaxies millions of light years away, we know that gravity is still at work, even though we cannot feel it directly. The force that binds the Milky Way together, that holds galaxies in their orbits, is gravity. But how can this force, so intricately tied to the fabric of space, act across such vast distances? The fact that we can measure and observe the effect of gravity across the universe suggests that gravity, in some sense, transcends the limitations of physical space. It is not bound by the same rules that govern other forces. Gravity seems to reach beyond space, acting as a universal constant, a binding force that holds everything together, no matter the distance. This paradox, how a force can stretch across the emptiness of space, how it can be so powerful yet so intangible, is what makes gravity such an enduring mystery. We know its effects, we feel it on Earth, and we observe its influence across the universe. But understanding how it works, why it behaves the way it does, and what role it plays in the greater cosmic scheme remains one of the greatest challenges in science. The more we discover about the nature of gravity, the more we realize that our understanding is only the beginning. The mysteries of gravity extend far beyond our current grasp, and as we continue to probe the depths of space, we will surely find that gravity holds even more secrets that could unlock the deepest truths about the universe itself. As we look up at the cosmos, at the galaxies swirling in space and the stars that burn within them, we are reminded of the power of gravity, the mysterious force that shapes everything, that guides the movements of celestial bodies and determines the structure of the universe. And as we stand on the edge of discovery, poised to explore the deepest corners of space, we are left with the central question: how can a gravity well exist in the void of space? The answer, as elusive as it is, holds the key to understanding the very nature of the universe. The classical view of gravity, Newton's legacy. The story of gravity begins with a man who, over 3 centuries ago, transformed our understanding of the universe. Isaac Newton, one of the most brilliant minds in history, revolutionized science with his law of universal gravitation. In his Philosophia Naturalis Principia Mathematica, published in 1687, Newton laid the groundwork for a new, unified understanding of how the universe operates. His insight into gravity as an invisible force acting at a distance became a cornerstone of classical physics, a theory so powerful in its simplicity that it would guide scientists for centuries. Newton's law of gravitation would be the blueprint that helped explain the movement of the planets, the behavior of falling objects, and the orbits of moons and stars. Newton's groundbreaking idea was that gravity is a universal force of attraction that acts between any two masses. According to Newton, gravity operates through an invisible force that acts instantaneously at a distance. If two objects were far apart in space, they would still exert a gravitational pull on one another, regardless of the intervening distance. Gravity, it seemed, was a force that transcended space itself. This idea was revolutionary, but it also posed a problem. Newton could describe how gravity worked, but he had no explanation for how it could operate across vast distances without a medium to carry the force. Unlike light, which travels through electromagnetic waves, or sound, which requires air to travel, gravity was acting instantaneously, despite the apparent void of space. There was no visible medium through which the force could be transmitted, and yet the force existed. Despite this, Newton's law of gravitation worked remarkably well. It could predict the motion of planets, the path of comets, and even the shape of Earth itself. But as elegant as Newton's theory was, it would soon become clear that gravity didn't always behave as expected, particularly when we encountered situations involving seemingly empty space places where no obvious mass was present to generate gravity. For instance, Newton's law of gravitation suggested that gravity existed wherever mass was found. Planets, stars, and moons all exerted a gravitational pull, but what about the vast stretches of space between them? These empty spaces between celestial bodies, while seemingly devoid of any material mass, were still subject to the effects of gravity. How could an invisible force act across the vacuum of space without any mass to produce it? This became apparent when astronomers and physicists began to study the behavior of gravity in more detail. For example, when Newton's law was applied to celestial bodies like the Moon, it was observed that while the Moon's orbit around Earth followed Newton's predictions with remarkable accuracy, the orbits of other planets, particularly those far from the Sun, did not. Some planets, like Mercury, showed small deviations from the expected path that Newton's laws could not fully explain. Moreover, the notion that gravity acts instantaneously at a distance seemed increasingly unsatisfactory. In a universe governed by the rules of classical physics, the idea that gravity could travel across vast distances without any delay seemed to conflict with the general understanding of how forces work. If gravity was truly instantaneous, what was the medium through which it traveled? Did it operate as a force that was felt across empty space the moment two objects were in each other's vicinity? This growing realization that Newton's theory did not account for all phenomena eventually led to deeper investigations into the nature of gravity. The most glaring contradiction came with the realization that space was not as empty as it seemed. It was revealed that gravity didn't just affect the visible material universe, it also seemed to stretch across vast, empty stretches of space, acting as if there were invisible connections between objects, no matter how far apart. The question then became, how does gravity behave in these vast voids where there is no obvious mass to produce the force? The key to this mystery lay in understanding the relationship between mass, space, and time. If Newton had established gravity as a force acting at a distance, it was clear that this force was felt universally, even in the empty spaces between celestial bodies. And this paradox, how gravity operates in places devoid of mass, would lead to the next great breakthrough in our understanding of the force. It was clear that the universe wasn't just a simple mechanical system of mass acting upon mass. Gravity, as described by Newton, was only part of the picture. The elegance of Newton's theory, with its ability to predict planetary motions and celestial mechanics, made it one of the greatest achievements of classical physics. But it was also clear that the classical model of gravity, where mass simply attracted other mass through an invisible force, was beginning to show cracks. The idea that gravity could act instantaneously across space without a medium and without any clear understanding of how gravity worked at greater scales posed philosophical and scientific questions that could no longer be ignored. In the centuries that followed, Newton's classical understanding of gravity would face challenges that ultimately led to a more sophisticated understanding of the force, one that transcended the simple notion of gravity as an invisible force between masses. The notion that gravity could operate instantaneously across space without any physical medium seemed increasingly implausible, and the quest for understanding the nature of gravity would become a journey into the very fabric of space and time itself. In summary, while Newton's law of universal gravitation provided a remarkably accurate framework for understanding how gravity works in the world of planets, stars, and moons, it also left behind questions that could not be fully answered. How does gravity work in the vast empty spaces between celestial bodies? How does it stretch across these voids without a medium? And, perhaps most perplexingly, how does gravity operate without a mechanism to transmit it? These questions laid the foundation for a revolution in physics that would ultimately change our view of the cosmos. As we now know, the answers to these questions would be revealed not by Newton, but by a later genius, Albert Einstein, whose theory of general relativity would replace the classical view of gravity and provide a new understanding of how the force behaves across space and time. However, it was Newton's timeless insights that set us on the path toward these revolutionary discoveries, and his legacy remains a cornerstone of our understanding of the universe, one that we continue to build upon as we deepen our understanding of the fundamental forces of nature. Einstein's revolution gravity as curved space-time, Isaac Newton's law of universal gravitation, was a monumental achievement. For over 2 centuries, it provided the framework for understanding the gravitational interactions that govern everything from falling apples to the orbits of planets. Yet, even as it elegantly explained the motion of celestial bodies, there were aspects of gravity that Newton's theory could not fully account for. The most profound of these was the question of what gravity really is. What force acts across vast distances of empty space and causes objects to attract one another? Newton had given us the equation to describe gravity's effect, but he left the deeper nature of the force largely unexplained. Enter Albert Einstein, a revolutionary figure whose theories of relativity would forever change the way we understand gravity. In 1915, Einstein unveiled his theory of general relativity, a profound shift in our understanding of how gravity worked. What Einstein proposed was nothing short of revolutionary. Gravity, he argued, is not a force at all, but rather the result of the curvature of space and time caused by mass. In Einstein's framework, the very fabric of the universe, which he called space-time, could be bent and distorted by the presence of matter. Objects move through this curved space-time, and it is this curvature that we perceive as gravity. To visualize this concept, imagine a massive object like a planet or a star sitting on the surface of a stretched-out fabric. The object doesn't just sit there, it bends the fabric around it, creating a well in the surface. Now imagine a small object like a marble rolling across the fabric. As it approaches the well, it is pulled toward the larger object, not because there is an invisible force pulling it directly, but because the fabric itself is bent in such a way that the marble follows a curved path. This analogy, though simplified, helps illustrate the basic idea behind Einstein's theory. Massive objects warp the space-time around them, and this warping is what we experience as gravity. In Einstein's theory, space and time are not separate, independent entities. They are fused together into a single, 4-dimensional continuum called space-time. Just as a massive object bends the fabric of space-time, so too do the dimensions of time itself become warped in the presence of mass. The stronger the gravitational field, the more massive the object, the more space-time is curved, and the more time itself slows down relative to regions of weaker gravitational influence. This realization led to the famous prediction of time dilation. Time passes more slowly near massive objects like stars and planets, and the effect becomes even more pronounced as one approaches the event horizon of a black hole. This concept of gravity as the curvature of space-time was a complete departure from the idea of gravity as a force acting at a distance. It fundamentally redefined how we think about the universe. Instead of imagining gravity as an invisible force that pulls objects toward each other, we now think of it as a manifestation of the way mass bends the very structure of space and time. This new way of looking at the universe allowed Einstein to make several profound predictions, many of which have since been confirmed through experimentation and observation. One of the most striking predictions of Einstein's theory was the bending of light in a gravitational field. According to Newton, light should travel in straight lines, unaffected by gravity. But Einstein's theory predicted that light too would follow the curvature of space-time. This means that light passing near a massive object, like the Sun, would be bent slightly as it traveled through the curved space-time around it. In 1919, a team of astronomers led by Arthur Eddington confirmed this prediction during a solar eclipse, observing that the stars near the Sun appeared to be slightly displaced from their expected positions due to the bending of light caused by the Sun's gravity. This was one of the first experimental confirmations of general relativity, and it sent shockwaves through the scientific community. Yet despite the success of Einstein's theory in explaining many phenomena, there remains a lingering mystery. Einstein's model predicts that gravity should only occur in the presence of mass, yet we observe inexplicable gravitational anomalies in regions that seem to be empty. This raises a new set of questions that challenges our understanding of gravity, mass, and space-time. One of the most striking examples of these anomalies is the observed behavior of galaxies and galaxy clusters. In the 1930s, astronomer Fritz Zwicky first noticed that the galaxies within clusters were moving much faster than would be expected based on the visible matter in those clusters. If the amount of visible mass was all there was, the galaxies should have been moving slower and should have begun to drift apart due to insufficient gravitational attraction, but they were held together, as if there were additional mass providing extra gravitational pull. Zwicky's observations led him to propose the existence of dark matter, an invisible substance that was responsible for the extra gravity. Since Zwicky's discovery, the evidence for dark matter has only grown stronger. Observations of galaxy rotations and gravitational lensing, the bending of light around massive objects, suggest that there is much more mass in the universe than we can see. However, the exact nature of this dark matter remains one of the greatest mysteries in physics. It is invisible, detectable only through its gravitational effects on visible matter. Yet, it is not the only anomaly that general relativity must contend with. A second anomaly occurs when scientists study the motion of galaxies at the edges of clusters. While dark matter accounts for some of the extra gravitational pull in galaxy clusters, there are still inconsistencies in how galaxies move in seemingly empty space. In fact, galaxies on the outskirts of large clusters are moving so fast that they should escape the cluster's gravitational pull entirely, yet they remain bound within it. This has led to the theory of dark energy, a mysterious force that is driving the accelerated expansion of the universe and possibly counteracting the effects of gravity on the largest scales. These gravitational anomalies challenge our current understanding of gravity, even within the framework of general relativity. If gravity is simply the result of curved spacetime, as Einstein predicted, then why do we see these inexplicable forces acting in regions where no visible mass exists? The growing body of evidence for dark matter and dark energy suggests that there are still elements of the universe that we do not fully understand, elements that are beyond the reach of our current theories. Could the bending of space-time in these unexplained regions be the result of unknown forces or hidden forms of matter? Or is gravity itself more complex than we currently imagine, perhaps interacting with other aspects of space-time that we have yet to discover? Einstein's general relativity provided us with a profound new understanding of gravity, one that still shapes our understanding of the cosmos today. Yet, as we peer further into the universe, the more we realize how much we still have to learn. Gravity, once thought to be a simple force of attraction, now appears to be part of a much larger, more intricate framework of space-time. It bends and warps the fabric of reality in ways that continue to surprise and challenge us, offering glimpses into the hidden workings of the universe. As we continue to explore these gravitational anomalies, the question remains, is Einstein theory the final word on gravity, or is there a deeper, more fundamental theory waiting to be discovered? Could gravity, in all its elegance and mystery, be a key to unlocking the greatest secrets of the cosmos? The answers to these questions may be hidden in the very fabric of space-time itself, and as we continue to explore, we move ever closer to understanding the true nature of the universe. The great mystery, gravity in empty space. Gravity is a force that governs the behavior of everything in the universe, from the fall of an apple to the dance of galaxies in the vastness of space. It pulls on objects, bending their paths and dictating their interaction. However, there is one question that has puzzled scientists for centuries. Why does gravity exist even in the vacuum of space, where there appears to be no mass to generate the force? This question stands at the heart of one of the greatest mysteries in modern physics. How does gravity work in the apparent absence of mass? As we peer into the cosmos, observing the galaxies, stars, and other celestial bodies, we are witnessing the effects of gravity at every scale. Planets orbit stars, moons circle planets, and entire galaxies are held together by gravity's invisible hand. But what happens in the vast, empty stretches between these objects in the deep voids of space? Can gravity operate where there is no visible matter, no stars or planets to exert an influence? In the classical view of gravity, which was formalized by Isaac Newton, the force of gravity is directly related to mass. Newton's law of universal gravitation states that every object with mass attracts every other object with mass. The force of gravity between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. This works perfectly well when we are dealing with celestial bodies like planets, stars, and moons, objects that contain measurable amounts of mass. However, in the vast, empty expanses of space, this law seems to encounter a significant problem. If there's no mass, how can there be gravity? The concept of a gravity well begins to offer some insights into this paradox. Imagine the fabric of space-time as a stretched-out sheet. Massive objects, such as planets or stars, create indentations or wells in this fabric, and smaller objects, like moons or satellites, fall into these wells, which we interpret as gravitational attraction. The gravity well of a star, for example, is what keeps planets in orbit around it. But in the empty void of space, where there are no stars or planets, does gravity still exist? And if it does, how does it exert its influence in the absence of visible mass? The concept of a gravity well is less intuitive. In these seemingly empty regions of space where no mass is present to create a well, we still observe gravitational anomalies, irregularities that defy the conventional wisdom that gravity requires mass to exist. These anomalies challenge the classical understanding of gravity, pushing us to reconsider what we know about the fundamental forces that shape our universe. One of the most notable examples of these anomalies can be found in the study of galaxy clusters. When astronomers began studying the motion of galaxies within these clusters, they noticed something strange. The galaxies in the outer regions of clusters were moving much faster than predicted. According to Newton's laws, the galaxies should have been slowly drifting away from the cluster, as there seemed to be insufficient visible mass to hold them together. However, they remained bound to the cluster, suggesting that there was an unseen force at work. This discrepancy led to the suggestion that there was an unseen form of mass, which we now call dark matter. This hypothetical form of matter does not emit light or other forms of electromagnetic radiation, making it invisible to telescope. However, its gravitational effects are measurable, and it seems to account for the additional gravitational pull needed to keep galaxies in their clusters. Yet, dark matter is still an elusive concept, and despite extensive searches, no one has yet directly detected it. Even more perplexing are the gravitational anomalies observed in regions of space that appear to have no mass whatsoever. These Anomalies suggest that gravity is operating in regions where there is no obvious source of mass to generate the force. For instance, scientists have observed gravitational lensing, a phenomenon where light from distant objects is bent as it passes through space. This bending, caused by gravity, occurs even in regions where there appears to be no mass to produce the gravitational pull. In these regions, the space-time fabric appears to be warped, yet no visible mass is responsible for the curvature. This leads us to the intriguing possibility that gravity might be influenced by factors beyond just visible matter. Could there be unseen forms of energy or matter, perhaps in the form of dark energy, that are subtly affecting the curvature of space-time? Dark energy, which is thought to make up about 68% of the universe, is an enigmatic force that is driving the accelerated expansion of the cosmos. It may, in some way, interact with space-time in a way that we have yet to fully comprehend, possibly influencing gravity in these empty regions. The observation of gravitational anomalies in deep space regions forces us to consider the possibility that our current theories are incomplete. If gravity operates in the vacuum of space, seemingly without any mass present, then there must be other hidden factors at play. This raises critical questions about the nature of space, gravity, and the universe itself. Could gravity be a more complex phenomenon, influenced not just by visible mass, but also by invisible forces or energy that we have not yet detected? Or is there something fundamental about the structure of space-time itself that we do not yet understand, something that enables gravity to function even in the absence of mass? These questions highlight the tension between observation and theory. On one hand, we have Newton's law of gravitation, which elegantly describes the behavior of gravity in the presence of mass. But on the other hand, we have these unexplained gravitational anomalies, which challenge the assumption that gravity is solely a force between masses. The more we observe, the more we realize that gravity's behavior in regions of space with little to no detectable mass cannot be fully explained by our current understanding. As scientists continue to probe these gravitational anomalies, they are not just investigating the nature of gravity itself, they are also exploring the very fabric of space-time, the fundamental structure that governs the universe. Understanding how gravity operates in the vacuum of space could lead to a deeper understanding of space-time, energy, and matter. It may even provide clues about the elusive dark matter and dark energy that seem to dominate the universe, but remain largely invisible to our instrument. The search for answers to these questions is not just a theoretical exercise, it has practical implications as well. Understanding gravity in regions of space with no visible mass could help us refine our models of the universe's structure and evolution. It could also lead to breakthroughs in technology, allowing us to better understand phenomena like black holes, gravitational waves, and the expansion of the universe. In conclusion, the mystery of gravity in empty space is one of the most fascinating and perplexing challenges in modern physics. The gravitational anomalies observed in regions devoid of visible mass suggest that there is much more to gravity than we currently understand. Whether the answer lies in the presence of unseen matter, the influence of dark energy, or some other hidden factor, the search for the truth is an ongoing journey that will shape our understanding of the universe for generations to come. Gravity, once thought to be a straightforward force, is now emerging as a key to unlocking the deepest mysteries of the cosmos, inviting us to explore the unknown and reconsider the very nature of reality. Dark matter, the invisible hand behind. The gravity well in the vast, silent expanse of space, there is an invisible force that shapes the motions of galaxies, holds clusters of stars together, and even influences the path of light. This force is gravity, and while we can easily observe its effects on the motion of celestial bodies, scientists have long been puzzled by the fact that these gravitational forces do not seem to match up with the amount of visible matter in the universe. In many regions of space, galaxies appear to be rotating too fast, or galaxy clusters too tightly bound for the amount of visible mass they contain. Something unseen, something invisible must be at play, and this is where the concept of dark matter enters the picture. Dark matter is one of the most profound mysteries in modern physics. It is the name given to a hypothetical form of matter that does not emit absorb, or reflect light, making it undetectable by traditional telescopes. It cannot be seen, touched, or directly measured. Yet, its existence is inferred by the gravitational effects it has on visible matter. Scientists believe that dark matter accounts for the missing mass in galaxies and galaxy clusters, where visible matter alone cannot explain the observed gravitational pull. In essence, dark matter seems to be the invisible hand shaping the gravitational field, pulling on stars, gas, and galaxies in ways that cannot be explained by ordinary matter alone. To understand the significance of dark matter, we must first delve into the way galaxies move. In the 1970s, astronomer Vera Rubin studied the rotation of galaxies and made a startling observation. The stars on the outer edges of galaxies were moving much faster than expected. According to Newtonian physics, the stars farther from the galaxy's center should be moving slower as the gravitational pull from the galaxy's mass weakens with distance. But Rubin found that even at the furthest reaches of the galaxy, the stars were maintaining high speeds, as if they were being held in place by an unseen force. This was a profound discovery, as it suggested that the visible matter, the stars, gas, and dust that we could see was not enough to account for the galaxy's behavior. Something else, something invisible, must be present in much greater quantities than we could observe. This was the birth of the dark matter hypothesis. If the extra gravitational pull was not coming from visible matter, it must be coming from an unseen source, one that did not interact with light in any detectable way. It was, quite literally, an invisible form of matter that exerted a gravitational influence on the visible universe. But how does dark matter fit into the larger picture of gravity? To explore this, we need to consider the concept of a gravity well. A gravity well is a region of space where the gravitational pull of a massive object distorts the fabric of space-time. The more massive the object, the deeper the gravity well. In our own solar system, the Sun creates a deep gravity well that keeps the planets in orbit. Similarly, in a galaxy, the combined gravitational pull of all the stars, gas, and other matter creates a gravity well that holds the galaxy together. However, when we measure the mass in a galaxy, we find that the visible matter alone doesn't create enough gravitational pull to keep the stars and other objects moving as they do. This is where dark matter comes in. Dark matter, scientists believe, is responsible for providing the extra mass that generates the gravitational pull needed to explain these anomalies. It is thought to be distributed throughout galaxies, forming a halo of invisible matter that surrounds the galaxy. This halo is where dark matter's gravitational influence is most profound. The presence of dark matter helps explain the faster than expected rotation of galaxies, as well as the movements of galaxy clusters, which would otherwise fly apart due to their own velocity. But while dark matter helps explain many of the gravitational anomalies observed in galaxies, it remains one of the most elusive and mysterious components of the universe. We still don't know exactly what dark matter is made of. It doesn't interact with light, so we can't detect it directly through telescopes. It doesn't interact with ordinary matter in any way that we can easily measure, except through its gravitational effects. This makes dark matter one of the most frustrating puzzles in modern science. It is present, we know that much, but it is invisible, detectable only through its interaction with gravity. The hunt for dark matter is one of the driving forces behind modern astrophysics. Scientists have proposed several candidates for what dark matter could be. The leading hypothesis is that dark matter consists of a type of particle known as WIMP, weakly interacting massive particles. WIMPs, if they exist, would be heavy particles that interact with normal matter via gravity and the weak nuclear force, but not through electromagnetism, which means they would be invisible to our current detection method. Experiments are underway around the world to detect these particles directly, either by observing their rare interactions with normal matter or by detecting the energy released when they annihilate each other. Another candidate for dark matter is axion, extremely light particles that may also interact only weakly with ordinary matter. Though no experiment has yet detected dark matter particles, the search continues as the existence of dark matter has profound implications for our understanding of the universe. The discovery of dark matter would be one of the greatest scientific breakthroughs of our time, shedding light on the unseen parts of the cosmos and offering a new understanding of how the universe works on the largest scales. However, even as we edge closer to uncovering the nature of dark matter, we are confronted with an even deeper question. Could dark matter be influencing the gravitational field in space, even when no visible mass is present? The gravitational effects of dark matter are apparent in galaxies and galaxy clusters, but what about in the vast, seemingly empty stretches between these galaxies? Does dark matter extend across the universe, influencing the curvature of space-time? Even in the absence of visible mass, if dark matter is indeed a fundamental component of the universe, could it be shaping the very fabric of space-time itself? These questions suggest that dark matter might not just be a passive player in the cosmic drama, but an active one, influencing the structure and behavior of the universe on a grand scale. It might be shaping the formation of galaxies, the growth of clusters, and the expansion of the universe itself. In this sense, dark matter is not just a missing component of the universe, but a key to understanding the fundamental forces that govern the cosmos. The existence of dark matter forces us to reconsider our understanding of the universe in a more profound way. We are accustomed to thinking of the universe as composed of visible, tangible matter stars, planets, galaxies, and everything in between. But dark matter suggests that there is a hidden, invisible layer to the universe, one that shapes the very fabric of reality without ever being seen. The implications of this are vast, not just for physics, but for philosophy as well. What does it mean to live in a universe that is made not just of what we can see, but of what we cannot? Does the invisible nature of dark matter suggest that there is more to the universe than meets the eye, that the universe is more mysterious and complex than we could ever have imagined? The search for dark matter is far from over, and as our understanding of the universe deepens, it will undoubtedly lead to even more questions. Are there other unseen forces at work, influencing gravity and the structure of space-time in ways we have yet to discover? Could dark matter be the key to unlocking other mysteries, such as the nature of gravity itself or the origins of the universe? As we continue to probe the unknown, we may find that the answers to these questions will reshape our understanding of the cosmos and of our place within it. The role of dark energy, the accelerating expansion of the universe as we've explored, the mysteries of gravity, dark matter, and the cosmic anomalies that challenge our understanding, we find ourselves faced with yet another perplexing force, one that has been described as the push behind the accelerating expansion of the universe. This force, dark energy, is perhaps even more enigmatic than dark matter, and it plays a critical role in shaping the fate of the cosmos. While dark matter helps explain gravitational anomalies at the galactic scale, dark energy is believed to be driving the universe's accelerated expansion, pushing galaxies away from each other at an increasing rate. Together, dark matter and dark energy form a cosmic tapestry, intertwining and influencing each other in ways that could one day offer a more complete understanding of gravity and the structure of the universe, especially in those regions of space where visible mass is scarce. To understand dark energy, we must first consider the implications of its discovery. In the late 1990s, two independent teams of astronomers using distant supernovae to measure the rate of the universe's expansion made an astonishing discovery. Not only was the universe expanding, but this expansion was accelerating. For nearly a century, scientists had assumed that gravity, which pulls matter together, would gradually slow the rate of expansion, eventually leading to a big crunch, a reversal of the Big Bang. But instead, the opposite was happening. Galaxies appeared to be moving away from each other faster and faster over time. This unexpected acceleration suggested the presence of a force counteracting gravity's pull, a force that was unknown at the time. That force dubbed dark energy, is now thought to constitute roughly 68% of the total energy content of the universe. Dark energy is thought to be a kind of anti-gravity, a repulsive force that causes space itself to stretch and expand, pushing galaxies apart. This expansion is not happening in localized pocket or near particular object. It is happening throughout the entire universe. While galaxies and galaxy clusters are still bound together by gravity, the space between them continues to grow, accelerated by the mysterious influence of dark energy. It's as if the very fabric of space is stretching, with galaxies carried along for the ride. This phenomenon has profound implications for our understanding of gravity. The tension between dark energy's repulsive force and the attractive nature of gravity adds complexity to the cosmic narrative. Gravity, the force that binds stars, planets, and galaxies together, is a force that works by pulling objects toward one another. Dark energy, on the other hand, seems to be pulling everything apart. For centuries, scientists believed that gravity was the only force shaping the dynamics of the universe, but dark energy has introduced a counteracting force that complicates this simple picture. Now, the universe seems to be caught in a delicate balance between these two forces, one attracting and the other repelling. This raises an intriguing question. How can both forces, one pushing and one pulling, coexist in the very fabric of space? The key to this question lies in the nature of space-time itself. Einstein's theory of general relativity tells us that space and time are not fixed backgrounds against which objects move. Instead, they are dynamic, shaped by the presence of mass and energy. When massive objects bend space-time, they create the gravity wells that we experience as gravitational pull. In this sense, both gravity and dark energy are part of the same fabric. They are forces that affect the geometry of space-time, but in opposite directions. Gravity, the force that draws objects together, warps space-time in such a way that objects move toward one another. Dark energy, however, seems to have the opposite effect. It is thought to exert a kind of pressure on space-time itself, causing it to stretch. This causes distant galaxies to move away from us, accelerating the expansion of the universe. Yet, unlike dark matter, which is believed to be concentrated around galaxies and clusters, dark energy is uniformly distributed throughout space, acting everywhere, even in the vast voids between galaxies. To visualize this, imagine the universe as a balloon with galaxies represented by dots on the surface. As the balloon inflates, the dots move farther apart from each other. This inflation is analogous to the expansion of the universe. However, in the case of the universe, this expansion is accelerating due to dark energy, meaning the galaxies move apart faster as time progresses. The fabric of space itself is stretching, driven by an unseen force. Dark energy's role in the expanding universe is still not fully understood. One of the leading theories, the cosmological constant, was first proposed by Einstein in 1917 as a term in his equations of general relativity to allow for a static universe. Although Einstein later discarded the idea after the discovery that the universe was expanding, the cosmological constant has been revived to explain dark energy. According to this theory, dark energy is a constant energy density that fills space homogeneously, causing the universe to expand at an accelerating rate. There are other theories as well, such as the idea that dark energy is related to quantum fluctuations in the vacuum of space, what some scientists refer to as vacuum energy. This concept suggests that empty space is not truly empty, but instead is filled with fleeting particles that appear and disappear, creating a kind of energy field that causes the acceleration of cosmic expansion. Another possibility is that dark energy could be tied to some form of exotic, unknown matter, or a new type of field that interacts with space-time in ways we have yet to fully comprehend. Regardless of its exact nature, the discovery of dark energy has radically altered our understanding of the universe's fate. The idea that the universe is expanding at an ever-increasing rate raises questions about the future of the cosmos. If dark energy continues to drive the expansion of space, the universe could eventually become a vast, dark and cold expanse, with galaxies moving farther and farther apart. This so-called Big Freeze is one possible end state for the universe, where stars burn out, galaxies drift away, and the universe becomes a place of darkness and isolation. On the other hand, if dark energy were to change in some way, the expansion of the universe could slow down or even reverse, leading to the Big Crunch, a collapse of the universe back into a singularity. The mystery of dark energy adds a new layer of complexity to our understanding of gravity and the universe itself. While dark matter accounts for the gravitational anomalies in galaxies and galaxy clusters, dark energy provides the answer to the puzzle of the accelerating expansion of the universe. Together, these two components form the unseen backbone of the cosmos, influencing everything from the structure of galaxies to the far-reaching expansion of the universe. Yet, despite their profound effects, both dark matter and dark energy remain invisible to our instrument. We detect them only through their gravitational influences and their effects on the large-scale structure of the universe. This cosmic tug-of-war between the attractive force of gravity and the repulsive force of dark energy forces us to reconsider how we think about the universe. What is the true nature of space-time, and how do these opposing forces interact with one another? Could there be even deeper, more fundamental forces at work, influencing the fabric of reality in ways we have not yet imagined? As we continue to study dark energy and dark matter, we may one day unlock the secrets of the universe's most profound forces. The discovery of these mysterious components of the universe has opened up new frontiers in cosmology and physics, offering tantalizing glimpses into the underlying structure of space and time. What we are learning about dark energy and its role in the accelerating expansion of the universe could ultimately reshape our understanding of the universe's origins, its future, and perhaps even the very nature of gravity itself. The quantum realm, gravity at the smallest scales. As we have journeyed through the universe from the large-scale structure of galaxies to the enigmatic forces of dark matter and dark energy, we now find ourselves at a critical juncture, the interface between the two pillars of modern physics, general relativity and quantum mechanics. These two theories, while both incredibly successful in their respective domains, seem to be at odds when it comes to gravity. General relativity describes gravity as the curvature of space-time caused by mass, and it works remarkably well on large scales, explaining the behavior of planets, stars, and galaxies. Quantum mechanics, on the other hand, governs the behavior of the smallest particles, operating with principles of uncertainty and wave-particle duality. Yet when we enter the quantum realm and attempt to understand gravity at the smallest scales, the smooth fabric of space-time in relativity and the inherent uncertainty in quantum mechanics collide, creating a deep paradox. This collision has profound implications for our understanding of gravity, especially in regions of space where both quantum effects and gravity are expected to be strong, such as near black holes or the earliest moment of the universe. At these extremes, the forces of gravity should be just as important as the quantum effects, but we don't yet have a theory that successfully combines the two. To explore this, we must delve into the tension between the smooth, continuous nature of space-time in general relativity and the discrete, probabilistic nature of quantum mechanics. The smooth curvature of space-time in general relativity in Einstein's general theory of relativity, gravity is not viewed as a force transmitted through space, but as a result of the warping or curvature of space-time itself. Massive objects like planets, stars, and even light create indentations in the fabric of space-time. This curvature dictates the motion of objects, from the orbits of planets around the Sun to the trajectory of light passing near a black hole. In essence, gravity is the manifestation of the way mass bends space and time, and objects move along the curves of this fabric. This concept works exceptionally well on large scales. The orbits of planets, the movement of galaxies, and the bending of light around massive objects all can be predicted with astonishing precision using the equations of general relativity. However, when we venture into the quantum world, the smooth, continuous nature of spacetime breaks down. The uncertainty of quantum mechanics. Quantum mechanics, the other pillar of modern physics, is a radically different theory. It governs the behavior of particles at the smallest scales, where uncertainty reigns supreme. In the quantum world, particles do not have definite positions or velocities until they are measured. Instead, they exist in a cloud of probabilities, described by wave functions that dictate the likelihood of finding a particle in a particular place or state. Additionally, quantum mechanics introduces the idea of wave-particle duality, the concept that particles, such as light and electrons, can exhibit both particle-like and wave-like behavior depending on how they are observed. The inherent uncertainty of quantum mechanics contrasts sharply with the smooth, predictable curvature of space-time described in general relativity. Whereas general relativity suggests that space-time is a continuous, smooth entity, quantum mechanics presents a universe where the smallest scales are unpredictable, governed by probabilistic events. This discrepancy is most apparent when we try to apply the concept of gravity to the quantum realm. At extremely small scales, such as the Planck length, around 10 to 3510, seed 3510-35 meters, the fabric of space-time is expected to be turbulent, perhaps even quantized, meaning that space-time may not be smooth at all, but instead made up of discrete units. Much like the way matter is made up of atoms, the quest for quantum gravity. The problem lies in trying to reconcile these two visions of reality. On one hand, we have the smooth, continuous model of gravity in general relativity, and on the other, the probabilistic, uncertain nature of quantum mechanics. As it stands, the two theories don't mesh, and attempts to combine them into a single theory, known as quantum gravity, have yet to yield a conclusive result. One of the biggest challenges is that the mathematical tools used in quantum mechanics and general relativity are incompatible. In quantum mechanics, forces are often mediated by particles, such as the photon for electromagnetic force. Gravity, however, doesn't appear to have a similar mediator. In the quantum world, we have the concept of virtual particles, short-lived particles that pop in and out of existence, transmitting forces between objects. If gravity is to be explained in quantum terms, there must be a particle that mediates gravitational interactions, and this particle is called the graviton. But as of now, no one has detected the graviton, and the mathematical framework to describe it remains elusive. Gravitational anomalies in the quantum realm at the quantum level. Some physicists believe that gravity might behave differently than we expect. There are phenomena in deep space and within the subatomic world that don't fully align with the predictions made by classical gravity. These include the gravitational anomalies we've seen in the motion of galaxies and the bending of light, which have led to hypotheses such as dark matter and dark energy. But what if the answer to these anomalies lies not in the invisible masses of dark matter, but in the very fabric of space-time itself, warped in ways we don't yet understand? Could quantum mechanics provide the missing link to understanding these gravitational effects in empty space? One possibility is that quantum fields might be influencing gravity in subtle ways that we have yet to discover. For example, quantum fluctuations in the vacuum. The spontaneous appearance and disappearance of particles could create ripples in space-time that influence gravity in ways we currently cannot measure. In this scenario, gravity could be mediated by quantum fields that stretch across the cosmos, subtly shaping the curvature of space-time at the smallest scales. The quest for a unified theory, the search for quantum gravity, is one of the most exciting and challenging frontiers in physics. Some approaches, such as string theory, propose that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings that exist in higher dimension. String theory suggests that the graviton could be one of the many types of particles that emerge from the vibrations of these strings. While string theory has yet to provide definitive answers, it has already led to remarkable insights into the nature of space-time and the forces that govern the universe. Another approach, loop quantum gravity, posits that space-time is composed of discrete chunks, or loop, rather than being a smooth continuum. In this model, gravity is quantized, much like other forces in quantum mechanics. This theory is still in its early stages, but it offers a potential path toward reconciling general relativity and quantum mechanics. Regardless of the approach, the ultimate goal is to develop a theory of quantum gravity that can explain how gravity operates at the smallest scales. This theory would have profound implications not only for our understanding of gravity, but also for our conception of the universe itself. It could provide answers to some of the deepest questions in physics. What happens at the center of black holes? How did the universe begin in the Big Bang? Is space-time fundamentally discrete or continuous? Bridging the gap, the tension between general relativity and quantum mechanics, between the smooth curvature of space-time and the probabilistic nature of quantum forces, is one of the most profound challenges in modern physics. As we continue to investigate gravity at the smallest scales, we are reminded that the universe is far more mysterious than we can fully comprehend. The quantum realm, with its uncertainty and complexity, may hold the key to understanding gravitational anomalies in empty space, offering insights into the hidden workings of the universe that we have yet to uncover. Perhaps as we continue to explore these fundamental questions, we will discover that the boundary between the large-scale and quantum realms is not as sharp as it appears. Gravity, the force that shapes the cosmos on the grandest scale, may be intertwined with the very fabric of the quantum world in ways that we have yet to understand. The answers to these questions may not only resolve the mysteries of gravity, but also unlock new truths about the nature of reality itself, transforming our understanding of the universe from the smallest particles to the largest galaxies. The cosmological constant, a fix for empty space. When Albert Einstein first proposed his theory of general relativity in 1915, he revolutionized our understanding of gravity. According to his groundbreaking equations, gravity was no longer a force acting at a distance, but rather a curvature of space-time caused by mass and energy. However, as elegant as his equations were, Einstein encountered a significant problem. In a universe that was thought to be static, neither expanding nor contracting, his equations predicted that space itself should be either collapsing under the influence of gravity or expanding outward. This was in direct contradiction to the prevailing belief at the time, which was that the universe was stable and unchanging. To resolve this contradiction, Einstein introduced a term into his equations, the cosmological constant. This was a mathematical addition designed to counteract the pull of gravity on large scales and keep the universe static. It represented a hypothetical energy density that filled empty space, providing a kind of repulsive force that balanced gravity's attractive force and maintained the universe's equilibrium. For years, this idea of a cosmological constant remained mostly theoretical, and Einstein himself referred to it as his biggest blunder after the discovery that the universe was in fact expanding. However, the cosmological constant has experienced a remarkable resurgence in modern cosmology, especially in the context of explaining the strange gravitational behavior observed in deep space. The cosmological constant and its return. In the late 1990s, astronomers made an unexpected discovery while studying distant supernovae. They found that instead of the universe's expansion slowing down, as was expected due to gravity, it was accelerating. This discovery suggested that there must be some force acting on the universe that counteracts gravity's pull, causing it to expand faster over time. This force was named dark energy, and it was proposed that dark energy constituted roughly 68% of the total energy content of the universe. The nature of dark energy remains one of the most profound mysteries in physics, but many theorists began to look at Einstein's cosmological constant as a potential explanation for this repulsive force, leading to its revival as a central element in modern cosmology. The cosmological constant can now be viewed as a form of dark energy, a constant energy density that permeates all of space. This vacuum energy acts as a repulsive force, pushing galaxies apart and driving the accelerated expansion of the universe. In essence, it suggests that empty space is not truly empty, but rather is filled with a kind of energy that resists the pull of gravity, ensuring the universe continues to expand. Understanding the role of the cosmological constant. The cosmological constant, as it is currently understood, provides a potential solution to one of the most puzzling observations. In modern cosmology, why does gravity appear to behave so strangely in the voids of space where visible mass is absent? In regions of space that seem empty, galaxies and other cosmic structures are still influenced by gravity, suggesting that something invisible is at work, while dark matter has been proposed to account for the gravitational anomalies observed. In galaxies, the cosmological constant may explain the behavior of gravity on much larger scales. If the universe is truly expanding at an accelerated rate, the cosmological constant could be a key factor in driving that expansion. As space itself stretches, the energy density associated with the cosmological constant remains constant, continuing to exert a repulsive force throughout the cosmos. This would explain why, even in seemingly empty regions of space, gravity seems to be acting in ways that we cannot directly explain by the presence of mass. In fact, it raises a more profound question. Could the universe itself be actively maintaining a gravitational field even in the absence of matter? A constant force. In an ever-expanding universe, the cosmological constant introduces a fascinating paradox in our understanding of the universe. On one hand, it represents a constant force that fills all of space, potentially providing an explanation for the gravitational anomalies observed in the vast stretches between galaxies. On the other hand, it forces us to confront the concept of an ever-expanding universe. The more we study the cosmos, the more we realize that the universe is not just expanding outward, it's expanding at an accelerating rate. The very fabric of space is stretching, and the cosmological constant through dark energy could be the force that drives this expansion. This raises the intriguing possibility that the universe itself might not be a passive, static entity, but an active, dynamic system that is constantly influencing its own evolution. In a sense, the cosmos is not simply unfolding due to the interactions of mass and gravity. It is actively maintaining its own expansion, pushing galaxies farther apart, and shaping the overall structure of the universe. If the cosmological constant truly represents a vacuum energy that is spread evenly across space, it could mean that space itself is an active participant in the universe's dynamic. This idea is in stark contrast to the classical view of gravity, where space is seen as a passive arena where forces act upon objects. In the case of the cosmological constant, space itself is not a passive backdrop, but is imbued with an energy that drives the behavior of the universe. This provides a new lens through which to view the expansion of the cosmos, suggesting that the fabric of space-time is far more dynamic and energetic than we ever imagined. The tension between gravity and dark energy. The cosmological constant, while providing a possible explanation for the accelerated expansion of the universe, also underscores a deeper tension between two fundamental forces, gravity and dark energy. Gravity, the force that binds matter together, works by attracting objects toward each other. It is responsible for the formation of galaxies, stars, and planets. But dark energy, as represented by the cosmological constant, does the opposite. It pushes objects apart, driving the expansion of the universe. This contrast between attraction and repulsion lies at the heart of the universe's evolution. The universe's history has been shaped by the balance between these two forces. After the Big Bang, gravity was the dominant force, pulling matter together to form galaxies and stars. But over the course of cosmic history, dark energy began to take hold, eventually overpowering gravity and driving the accelerated expansion of the universe. This shift has profound implications for the future of the cosmos. If dark energy continues to dominate, the universe will continue to expand forever, with galaxies moving farther apart, stars burning out, and the universe growing colder and darker. This cosmic tug-of-war between gravity and dark energy adds complexity to our understanding of the universe's structure. While gravity is pulling objects together, dark energy is pushing them apart. This dynamic tension is what shapes the universe at the largest scales, from the growth of galaxy clusters to the expansion of the cosmos itself. Philosophical implications. The universe maintaining itself, the introduction of the cosmological constant. brings us to a philosophical crossroads. If the universe is indeed expanding at an accelerating rate, driven by the repulsive force of dark energy, does this imply that the universe is actively maintaining itself, constantly pushing against the forces that would otherwise pull it back together? The concept of a self-sustaining universe, one in which space itself exerts a force that drives its own evolution, challenges our traditional notions of causality and forces. Could it be that the very fabric of the universe is imbued with an intrinsic energy, an energy that not only shapes the gravitational field, but also drives the expansion of the cosmos? If so, the cosmological constant could be seen not just as a fix for empty space, but as a fundamental aspect of the universe's design, an invisible force that maintains the universe's equilibrium, even in the absence of visible matter. Indeed, this light, the cosmological constant, becomes not just a scientific concept, but a doorway into understanding the universe's deepest mysteries. It forces us to reconsider the nature of space itself, as well as the balance of forces that govern the cosmos. The question of whether the universe is actively maintaining its own gravitational field, even in regions devoid of mass, leads us to reconsider our understanding of reality and the very structure of existence. Conclusion: the cosmological constant has emerged as one of the most significant concepts in modern cosmology, offering a possible explanation for the strange gravitational behavior observed in empty space and the accelerating expansion of the universe. While the cosmological constant was originally introduced by Einstein to fix a static universe, it now provides a crucial piece of the puzzle in understanding the universe's ongoing evolution by introducing a constant energy density that fills all of space. Dark energy, as described by the cosmological constant, offers a solution to the mysteries of the universe's expansion. It challenges our conception of space and time, suggesting that the universe may not be a passive backdrop, but an active participant in its own expansion. As we continue to explore the implications of the cosmological constant and dark energy, we are confronted with deeper questions about the nature of gravity, the universe's future, and the forces that shape our reality. The universe, it seems, is far more complex than we could ever have imagined, with invisible forces at play that push and pull on the very fabric of space-time. The cosmological constant might not just be a fix for empty space, it could be the key to understanding the future of the cosmos itself. Wormholes and theoretical gravity, wells in the vast, seemingly empty stretches of space where the gravitational effects of visible mass are not immediately apparent. Scientists have long been grappling with anomalies that defy explanation. Galaxies move in ways that cannot be fully accounted for by the visible matter we can observe. Gravitational lensing bends light in regions where we expect to see nothing. Could these phenomena be the result of exotic, hypothetical constructs, tunnels through space-time known as wormholes that might exist in the emptiness? These theoretical passages through space-time offer an intriguing potential explanation for gravity anomalies that seem to defy the normal laws of physics. Though wormholes have yet to be proven, the possibility that they could exist raises profound questions about the nature of gravity and the structure of the universe. What are wormholes? Wormholes are, in essence, shortcuts through space-time. Imagine space-time as a vast, two-dimensional sheet. Normally, to travel from one point to another, you would move along the surface, following the curvature of space-time. But a wormhole proposes a different approach. Instead of moving through space-time, you could fold the sheet, creating a direct path between 2 points. This shortcut through space-time is what we call a wormhole, a theoretical tunnel that connects distant regions of the universe, bypassing the intervening space. The concept of wormholes arises naturally from Einstein's theory of general relativity. According to the equations of general relativity, massive objects bend and distort space-time. In theory, this bending could create a tunnel-like structure, a wormhole that links two separate regions of space-time. These wormholes, if they exist, could potentially offer an extraordinary way to travel vast distances in the universe. A trip from one galaxy to another, for example, could be completed in a fraction of the time it would take light to travel. bypassing the vast emptiness of space between them. Wormholes were first proposed by physicists Albert Einstein and Nathan Rosen in the 1930s. They explored the possibility of a bridge-like connection between two separate regions of space-time, a concept now known as the Einstein-Rosen bridge. Though initially considered a theoretical curiosity, wormholes have since become an important part of speculative physics, offering tantalizing possibilities for both theoretical physics and science fiction. While wormholes are still purely hypothetical, their implications are profound not just for space travel, but for understanding the fundamental nature of gravity. Wormholes as gravity wells in empty space. One of the most fascinating aspects of wormholes is their potential to create localized gravity wells in otherwise empty space. In general relativity, a gravity well is the curvature of space-time around a massive object, such as a planet, star, or black hole. This curvature, or well, dictates how objects move under the influence of gravity. A wormhole, by connecting distant points in space-time, would inherently create a kind of localized gravity, well, a region where space-time is significantly warped. However, in contrast to the gravity wells created by massive objects like stars or black holes, these gravity wells would exist in regions of space that appear to be devoid of visible mass. In fact, wormholes could, in theory, offer an explanation for the gravitational anomalies we observe in deep space. If these anomalies are the result of hidden or undetectable structures, wormholes could be the missing piece in understanding the gravitational forces at play in these seemingly empty regions. Could it be that the unexplained gravitational effects we see in deep space, the unusual motion of galaxies, the bending of light, the high velocities of objects in galaxy clusters, are the result of wormholes, localized disturbances in space-time that we cannot directly observe, but whose gravitational influence is still detectable? These potential connections between distant regions of the universe could explain why gravity appears to behave unexpectedly in areas where no obvious mass is present. The presence of a wormhole in an empty region of space might create a gravitational anomaly, influencing the movement of galaxies, stars, and even light without the need for any visible matter. Theoretical constructs versus observational anomalies. Despite their compelling theoretical foundation, wormholes remain speculative at best. There is no empirical evidence for the existence of wormholes. They have yet to be detected or observed in any way. The gravitational anomalies observed in deep space, which seem to suggest the presence of unseen mass or structures, could very well be explained by other, more conventional theories, such as the existence of dark matter or the influence of dark energy. It is also possible that the gravitational effects we observe are the result of some other unknown phenomenon that does not require the existence of wormholes at all. The contrast between the speculative nature of wormholes and the empirical observations of gravity anomalies in distant space raises an important question. Could we be witnessing the presence of these exotic phenomena, or are wormholes merely a theoretical construct to explain what we can't yet fully comprehend? While wormholes provide an exciting framework for understanding these gravitational mysteries, we are still far from being able to prove their existence or determine whether they are responsible for the anomalies we observe. One of the biggest challenges in detecting wormholes is that they would, by definition, be hidden in plain sight. A wormhole might not look like a traditional object, such as a star or a planet, and would likely be invisible to telescopes. The only clue we might have of a wormhole's presence would be its gravitational influence on nearby objects, which might manifest as unexplained movements or bending of light. In this sense, wormholes could be lurking in the background, influencing the universe in ways we cannot yet fully measure or understand. Theoretical challenges in wormhole detection are: if wormholes do exist, detecting them is an extraordinary challenge. According to Einstein's equations, wormholes could, in theory, be stable under certain conditions, but they would likely require enormous amounts of energy or exotic matter to maintain their structure. For a wormhole to remain open and traversable, it would need some form of exotic material with negative energy density to counteract the immense gravitational forces that would otherwise collapse the tunnel. This exotic matter is purely hypothetical and remains one of the key challenges in both theoretical physics and cosmology. In addition, the idea that wormholes could exist in regions of space that appear empty presents another complication. Since wormholes are believed to involve extreme warping of space-time, they could potentially distort the fabric of the universe in ways that are difficult to detect with current observational tools. For instance, the presence of a wormhole might create gravitational lensing effects, the bending of light around the wormhole, similar to the way massive objects like galaxies and black holes bend light. But distinguishing the effects of a wormhole from those caused by ordinary matter or other gravitational influences would be incredibly difficult. Could wormholes change our understanding of gravity? The idea of wormholes raises more than just scientific questions. It also forces us to reconsider the very nature of gravity and space-time. If wormholes exist, they would represent a dramatic shift in our understanding of the universe. The concept of shortcuts through space-time implies that the fabric of space is not as rigid and fixed as we once thought. Instead, space could be fluid, malleable, and capable of being bent in ways that we cannot yet comprehend. This opens up new possibilities for thinking about the universe as a dynamic, interconnected whole, where distant regions of space might be far more accessible than we previously imagined. If wormholes are real, they might allow for faster-than-light travel, offering a potential means of exploring the farthest reaches of the universe without having to traverse the vast emptiness between. But beyond their potential practical applications, wormholes could fundamentally change how we understand the flow of time and gravity. Space-time, as we know it, may not be a continuous and static entity. Instead, it could be a complex and ever-changing structure, with wormholes acting as conduits that connect disparate parts of the universe in ways that defy conventional understanding. The mystery of wormholes remain one of the most exciting and speculative ideas in theoretical physics. While they offer a potential explanation for gravity anomalies in seemingly empty space, they also challenge our current understanding of the universe. The tension between the theoretical nature of wormholes and the empirical observations of gravitational anomalies forces us to confront the limits of our knowledge. Are we witnessing the effects of these exotic phenomena, or are they merely an elegant construct to explain the mysteries of the universe? As we continue to explore the cosmos and investigate the strange gravitational behaviors in deep space, the concept of wormholes offers a tantalizing glimpse into a new frontier of physics, one that could ultimately reshape our understanding of space, time, and gravity. The edge of our knowledge, the limits of current physics, as we push the boundaries of our understanding, both in the vast expanse of the cosmos and within the smallest quantum realms, we find ourselves facing an uncomfortable truth. Our current models of physics, while revolutionary, are incomplete. They have served us remarkably well in describing a vast array of phenomena, from the fall of an apple to the motion of planets, but there are gaps, significant ones, where our understanding falters. The gravity anomalies we observe in empty space, the behavior of distant galaxies, the strange influence of dark matter and dark energy, and the puzzles at the intersection of quantum mechanics and general relativity all point to the same fundamental question. Are the laws of physics as we know them truly the final word on the nature of the universe? Or are we witnessing the limitations of our understanding, a glimpse of something far deeper and more mysterious that could forever challenge the very foundations of physics? Classical physics and its limitations. The story of modern physics began with the laws of classical mechanics, which were largely based on the work of Isaac Newton. His law of universal gravitation provided a framework for understanding how masses interact with each other through gravity. It was a groundbreaking theory that worked remarkably well for centuries, explaining everything from the orbits of planets to the motion of falling objects. However, as we ventured further into the cosmos and into the quantum realm, we began to notice that Newton's laws, despite their elegance and utility, were not enough to explain all the phenomena we observed. The most glaring example of this came with the advent of relativity. In the early 20th century, Albert Einstein's special and general theories of relativity revolutionized our understanding of space and time, replacing the classical Newtonian view. According to Einstein, gravity is not a force transmitted through space, as Newton had described, but a warping or curvature of space-time itself caused by mass and energy. General relativity works incredibly well in describing large-scale cosmic phenomena such as the orbits of planets, the behavior of light near black holes, and the dynamics of galaxies. Yet despite its incredible success, even Einstein's theory falls short in certain extreme environments. The breakdown of general relativity, while groundbreaking, encounters significant problems when we attempt to apply it to the quantum realm. At the scales of atoms and subatomic particles, gravity doesn't behave in the way general relativity predicts. The smooth curvature of space-time breaks down, and quantum effects, such as uncertainty and wave-particle duality, dominate. The classical descriptions of space-time and gravity become ineffective, and we are left with a world where the laws of physics seem to work differently. One of the most profound contradictions arises at the center of black hole. General relativity predicts that when a massive star collapses, it will form a singularity, a point of infinite density where space-time curves infinitely. At this point, the equations of general relativity break down, and we are faced with the paradox of infinite density and zero volume. This suggests that our understanding of gravity and space-time reaches its limit in these extreme conditions, and general relativity is unable to provide a complete picture of what happens inside a black hole. While quantum mechanics has been incredibly successful in explaining the behavior of particles at microscopic scales, it fails to account for gravity, and its application to black holes only deepens the mystery. Quantum mechanics and the struggle with gravity. Quantum mechanics, on the other hand, deals with the fundamental particles that make up matter and energy. It describes a universe in which uncertainty and probability reign, where particles can exist in multiple states simultaneously and interact in strange, seemingly paradoxical ways. In the quantum realm, gravity appears as an anomaly. The force of gravity is exceedingly weak compared to other forces like electromagnetism, and there's no obvious quantum description of how gravity works. While quantum mechanics has been extraordinarily successful in explaining phenomena at the atomic and subatomic levels, its inability to incorporate gravity is one of its major shortcomings. The standard model of particle physics, which describes the fundamental particles and forces of the universe, excluding gravity, does not include a quantum theory of gravity. The search for a quantum theory of gravity, one that reconciles the smooth fabric of space-time in general relativity with the probabilistic nature of quantum particles, is one of the holy grails of modern physics. Theoretical attempts, such as string theory and loop quantum gravity, have proposed ways to combine these frameworks, but so far, no definitive theory has emerged. The tension between observation and theory. At the heart of the puzzle is the tension between the observable facts and the theoretical models that attempt to explain them. On one hand, we have the empirical observations, the behavior of galaxies, the motion of stars, the bending of light, and the strange gravitational anomalies we see in deep space. On the other hand, we have the theoretical models, such as general relativity and quantum mechanics, that offer explanations for the forces governing the universe. But when we look at phenomena that lie at the intersection of both theories, such as black holes or the accelerating expansion of the universe, neither framework is enough to provide a complete explanation. For example, the discovery of the accelerated expansion of the universe in the late 1990s, attributed to dark energy, challenged the existing theories of gravity. In classical physics, gravity is always an attractive force, one that slows down the expansion of the universe. The idea that the expansion could actually be accelerating due to an invisible force was an enormous puzzle. Dark energy, which was posited as the driving force behind this acceleration, has no direct counterpart in the laws of physics as we currently understand them. It adds a layer of complexity to our already incomplete models, suggesting that there may be aspects of the universe and the forces at play within it that we have yet to comprehend. Similarly, the gravitational anomalies observed in galaxies and Galaxy clusters, which point to the existence of dark matter, present a challenge. Dark matter is theorized to account for the extra mass required to explain these gravitational effects, but it has never been directly detected. Its presence is inferred solely through its gravitational influence on visible matter, yet it remains an invisible, enigmatic component of the universe, its properties unknown. Theories about dark matter abound, but as of now, it remains one of the greatest unsolved mysteries in cosmology. Theoretical physics at the edge of knowledge. These unresolved questions reveal the limits of current physics and the need for a more unified theory. The tension between quantum mechanics and general relativity, the uncertainty surrounding dark energy and dark matter, and the inability of both classical and quantum models to explain certain cosmic phenomena all point to a deeper problem. Our current understanding of the universe is incomplete. The laws of physics, as we know them, seem to be limited in their ability to describe the full complexity of the cosmos. This is where the frontier of modern physics lies, at the edge of our knowledge, where new paradigms may emerge. The search for a theory of quantum gravity, a framework that can successfully merge the smooth curvature of space-time in general relativity with the probabilistic nature of quantum mechanics, is one of the most pressing challenges. String theory, loop quantum gravity, and other proposed models are all steps in the right direction, but the ultimate answer remains elusive. Is the universe telling us something fundamental? Could we be witnessing a glimpse of something fundamentally new that challenges the very laws of physics as we know them? The unanswered questions about gravity, dark matter, dark energy, and the unification of quantum mechanics and general relativity suggest that there may be deeper truths yet to be discovered, truths that transcend our current understanding of the universe. The mysteries that remain, the accelerating expansion of the universe, the gravitational anomalies in empty space, the strange behavior of black holes, could be revealing something profound about the nature of reality itself. As we continue to probe these cosmic puzzles, we are faced with a humbling realization. The universe is far more complex than we could have imagined. What we once thought were definitive answers, the laws of gravity, the nature of space and time, the structure of matter, may only be approximations of a deeper, more intricate reality. The future of physics lies at the intersection of observation and theory, where new discoveries may force us to rethink everything we thought we knew about the universe. The limits of current physics in explaining the gravity wells in empty space, as well as the broader cosmic phenomena that challenge our understanding, highlight the profound mysteries that remain at the heart of modern science. Theoretical models, while incredibly successful in describing the universe on certain scales, fail to provide a comprehensive framework for the universe as a whole. As we explore the edge of our knowledge, we are confronted with the possibility that the laws of physics we currently rely on are incomplete, that the true nature of the universe may be far stranger and more complex than we can even begin to understand. The unanswered questions about gravity, dark matter, dark energy, and the unification of quantum mechanics and general relativity invite us to keep pushing the boundaries of what we know. As we continue to explore the cosmos, we may one day find the deeper truths that unite the forces of nature and unlock the mysteries of the universe. Until then, we remain on the edge of our knowledge, striving to understand a universe that continues to surprise us with its complexity and wonder. The multiverse hypothesis, gravity beyond our universe. The universe as we know it is vast, almost incomprehensibly so, stretching across billions of light years, filled with galaxies, stars, and black holes. For centuries, the very idea that anything beyond our observable universe could exist was purely speculative. The laws of physics, including gravity, governed everything we observed, providing an elegant framework for understanding the motion of celestial bodies and the formation of galaxies. But as we peer deeper into the cosmos, grappling with the gravitational anomalies we observe in seemingly empty space, we are faced with an unsettling possibility. What if these anomalies, these inexplicable gravity wells, are not just the result of visible matter, but are caused by gravitational influences from other universes? This speculative idea, the multiverse theory, suggests that our universe might not be the only one. What if there are other universes coexisting with our own, each with its own set of physical laws, constants, and properties? And if this is true, could the gravitational fields of these other universes be bleeding into ours, creating the gravitational anomalies we see in the distant reaches of space? This theory pushes the limits of imagination and challenges the very foundations of physics, suggesting that the universe we know may be only one of many, each with its own strange and incomprehensible influences. A brief overview, the concept of the multiverse. The idea that there are multiple universes beyond our own has a long and complex history in both philosophy and theoretical physics. It is not a new idea, but recent advancements in cosmology, quantum mechanics, and string theory have brought the multiverse back into the spotlight. The multiverse hypothesis proposes that our universe is just one of many, potentially infinite, universes that exist in parallel with one another. These universes could be similar to ours with comparable physical laws, or they could be radically different, governed by entirely different sets of principles. Some versions of the multiverse theory suggest that each universe is part of a larger, infinite bubble, with each universe forming from its own Big Bang. Others, like the many worlds interpretation of quantum mechanics, suggest that every quantum event, every decision, every possibility spawns a new universe, creating a branching tree of realities. While the multiverse theory has not yet been proven, it has gained traction among certain physicists, particularly those working in the fields of cosmology and string theory. These scientists have found that the multiverse hypothesis may offer explanations for certain unresolved questions in physics, including the fine-tuning of the constants of nature and the mysterious behavior of dark energy and dark matter. But one of the most fascinating implications of the multiverse theory is that it could offer an explanation for the gravitational anomalies we see in seemingly empty space. A glimpse of other universes. Over the years, astronomers and cosmologists have made a series of puzzling discoveries about the nature of gravity. In regions of space that appear to have little or no visible matter, gravity seems to behave in unexpected ways. Galaxies appear to move faster than they should. The orbits of stars and galaxies sometimes deviate from predictions, and the bending of light, a phenomenon called gravitational lensing, is observed in areas where no large object should be present. These gravitational anomalies have led scientists to hypothesize the existence of dark matter and dark energy, unseen forces that may be influencing the behavior of gravity across vast distances. But what if these anomalies aren't just the result of unseen mass or energy? What if they are the result of gravitational influences from other universes whose gravitational fields are bleeding into our own? This idea, though speculative, offers a fascinating possibility. If multiple universes exist and if they are somehow connected or interacting, then the gravity from these universes could spill over into ours, creating the strange gravitational wells and anomalies that we observe. In this model, the observable universe with all its galaxies, stars, and black holes might be just one bubble in a much larger and more complex multiverse. Each of these bubbles could have its own set of physical laws and constants, but they might still interact with each other in subtle ways, influencing one another through gravity. The gravitational field of a neighboring universe might affect the curvature of space-time in our own, creating the invisible wells of gravity that we see in distant galaxies or in the voids between cosmic structures. The nature of gravity in the multiverse, in a universe where multiple realities exist, each with its own set of physical laws, gravity might not be the simple force we think it is. The traditional view of gravity, as proposed by Isaac Newton and later expanded upon by Albert Einstein, is that it is a force of attraction between masses acting across space-time. This view works well on large scales, explaining the motion of planets and galaxies. But if the multiverse theory is correct, and if multiple universes are interacting with one another, gravity may not be a force that is confined to a single universe. Instead, it might be a more fundamental property of space-time itself, one that transcends individual universes and connects them in ways we cannot yet comprehend. In this speculative scenario, gravity could be more than just a force that governs the motion of objects within our universe. It could be a bridge connecting multiple realities. If the gravitational fields of other universes are bleeding into ours, it could explain some of the gravitational anomalies we observe, such as the unexplained motion of galaxies or the bending of light in regions where no visible mass is present. This raises the possibility that our universe is not a self-contained system, but is instead part of a larger, interconnected web of universes, each exerting its own gravitational pull on the others. The limits of our understanding, theoretical versus empirical, the idea that gravitational anomalies could be the result of influences from other universes, challenges the very foundations of physics. The speculative nature of this hypothesis forces us to confront the limitations of our current understanding. Our best models of gravity, both classical and quantum, are confined to a single universe, and they do not account for the possibility of parallel realities interacting with one another. While the multiverse hypothesis offers intriguing possibilities, it is still very much a theoretical construct. As of now, there is no empirical evidence to suggest that other universes exist, let alone that they are interacting with our own. The gravitational anomalies we observe could still be explained by other factors, such as the presence of dark matter, dark energy, or undiscovered forces in our own universe. The tension between theoretical models and observational data forces us to reconsider what we know about gravity, space-time, and the universe itself. Furthermore, the multiverse hypothesis raises profound philosophical questions about the nature of reality. If multiple universes exist, each with its own set of physical laws, then our universe and everything within it could be just one realization of vast and infinite set of possibilities. The very idea that there could be universes beyond our own, each with its own version of gravity and space-time, challenges our assumptions about the uniqueness of our universe and the nature of existence itself. The role of gravity in a multiverse. If the gravitational anomalies we observe are indeed the result of interactions with other universes, this would fundamentally alter our understanding of gravity. Gravity, in this model, would no longer be a force that exists solely within the confines of our own universe. Instead, it could be a universal force, one that links multiple universes together. The gravitational field of another universe might affect the curvature of space-time in our own, creating the gravitational wells and anomalies that we see. This would suggest that gravity is not merely a property of matter within our universe, but a more fundamental feature of the multiverse as a whole. This raises even more profound question. Could gravity be a bridge that connects not just our universe to other universes, but also different versions of reality within our universe? Could the fundamental nature of space-time itself be more malleable than we ever imagined, allowing for the possibility of traveling between universes or experiencing different versions of reality? These speculative ideas challenge the very nature of space, time, and gravity, and they push the boundaries of our imagination. A new frontier in physics, the possibility that the gravitational anomalies we observe in deep space could be the result of influences from other universes, forces us to confront the limits of our current understanding of physics. The multiverse hypothesis offers a tantalizing glimpse into a reality far beyond our own, where gravity is not confined to a single universe, but is a force that spans multiple realities, each with its own laws of physics. While this idea remains speculative, it challenges us to think beyond the constraints of our universe and to explore the possibility that the universe we know is not the only one that exists. As we continue to explore the mysteries of gravity, dark matter, dark energy, and the universe itself, we may one day find evidence that supports the multiverse hypothesis. Until then, we are left with a profound question. Are we truly witnessing the effects of other universes, or are we simply grappling with forces and phenomena that are beyond our current comprehension? The search for answers to these questions will push the limits of scientific knowledge and expand our understanding of the cosmos in ways we can hardly imagine. The gravity mystery that will define the future. As we have journeyed through the mysteries of gravity, dark matter, dark energy, and quantum mechanics, we are left with a central question that continues to perplex us. What is the true nature of the gravity wells we observe in empty space? These anomalies, observed in distant galaxies and vast stretches of seemingly void regions, suggest that gravity is behaving in ways that current models cannot fully explain. From the gravitational anomalies observed in galaxy clusters to the potential influence of dark energy, we have explored several possible explanations. Yet despite the advances in our understanding of the universe, the ultimate cause of these strange gravity wells remains elusive. Throughout this exploration, we have seen how various theories have emerged to explain these anomalies. Dark matter, which was proposed to account for the extra mass required to explain the gravitational effects observed in galaxies and clusters, offers one possible solution. Dark energy, the mysterious force thought to drive the accelerating expansion of the universe, provides another piece of the puzzle, suggesting that the fabric of space itself is not static but dynamically expanding. Quantum mechanics, with its uncertainties and probabilistic nature, raises the possibility that gravity could behave differently on the smallest scales, where quantum effects dominate. And of course, the speculative realm of the multiverse offers yet another tantalizing possibility, suggesting that the gravitational anomalies we observe could be the result of influences from parallel universes beyond our own. Despite the many ideas we have explored, the truth remains just out of reach. The current models of physics, while revolutionary, are clearly incomplete. As we stand on the edge of our knowledge, we are faced with the reality that gravity, space, and the very fabric of the universe may be far more complex than we ever imagined. The question remains, what is truly causing these strange gravity wells, and how does this fit into our broader understanding of the universe? A tapestry of theories. Each of the theories we've discussed, dark matter, dark energy, quantum gravity, and even the speculative multiverse, offers a unique perspective on the problem, but none of them provides a complete answer. Dark matter, despite its compelling gravitational effects, has yet to be detected directly. Its existence remains inferred, not observed. Dark energy, while explaining the acceleration of the universe's expansion, remains a mysterious and poorly understood force that cannot be fully described by current physical theories. Quantum gravity, the long-sought attempt to merge quantum mechanics with general relativity, has yet to yield a coherent, empirical framework. These gaps in our understanding are not just intellectual challenges, but profound questions about the very nature of reality. If gravity can behave unpredictably in certain regions of space, if the fabric of space-time can be bent and shaped in ways that we cannot fully explain, then what does this say about the universe itself? Are we on the brink of discovering a new set of laws that govern the cosmos? Laws that could radically alter everything we know about gravity, space, and time? The role of observation and experimentation. One of the most exciting aspects of modern physics is that, despite the theoretical challenges, new observational tools and experimental techniques continue to push the boundaries of what we can measure and understand. Gravitational wave observatories, such as LIGO and Virgo, are giving us a new way to observe the universe, allowing us to measure the ripples in space-time caused by massive cosmic events like black hole mergers. Observations of the cosmic microwave, background, CMB radiation, and the mapping of dark matter through gravitational lensing continue to provide clues about the unseen components of the universe. However, there is still much that remains beyond our current observational reach. While we have observed the effects of dark matter and dark energy indirectly, we have not yet been able to detect them directly. The search for a quantum theory of gravity, one that can explain the small-scale behavior of gravity, continues to be a central pursuit in theoretical physics, and the multiverse theory, while fascinating, remains speculative, with no direct evidence to confirm the existence of parallel universes. The tension between observation and theory has never been more apparent. As we gather more data, we realize that the laws of physics that have served us so well in the past might not be the final word on the nature of the cosmos. The mysteries we face, from gravitational anomalies to the behavior of dark energy, suggest that our current understanding is only a stepping stone toward a much deeper and more profound theory of everything, the evolution of our understanding. As we reflect on the journey we've taken, it becomes clear that our understanding of the universe is a constantly evolving story. From the early days of classical physics, where Newton's laws of motion and gravity seem to explain everything, to Einstein's revolutionary theory of general relativity, and now to the speculative ideas of dark matter, dark energy, and quantum gravity, the landscape of physics has shifted dramatically. Each discovery has not only answered questions but has also raised new ones, pushing us to rethink the very nature of reality. The pursuit of understanding gravity, especially in regions of space where it seems to behave strangely, has revealed that our universe is far more intricate and mysterious than we could have ever imagined. Theories about the nature of space-time, the forces that govern it, and the fundamental particles that make up the universe are constantly being refined. The more we learn, the more we realize that we are still only scratching the surface of the deeper truths that lie beyond our current model. A new revolution in physics? As we continue to grapple with the unresolved mysteries of gravity, dark matter, and dark energy, we stand on the precipice of what could be a new revolution in physics. The discovery of a unified theory, one that can reconcile the smooth curvature of space-time in general relativity with the probabilistic nature of quantum mechanics, could forever change our understanding of gravity. The identification and detection of dark matter and dark energy, if they can be directly observed, could provide profound insights into the invisible components of the universe, and the potential discovery of wormholes, the realization of parallel universes, or the detection of new exotic forces could expand our understanding of the cosmos in ways we cannot yet predict. The mystery of the gravity wells in empty space and the broader gravitational anomalies we observe across the universe represents one of the most profound challenges in science. Solving this mystery may not only revolutionize physics, but could also answer some of humanity's most fundamental questions. What is the nature of space-time? How did the universe come to be? Are we alone in the cosmos? Or is there more out there, perhaps in parallel realities? These questions are not merely theoretical musing. They are at the heart of our quest to understand the universe and our place within it. A glimpse into the unknown. As we look to the future, we are reminded that we are standing on the threshold of discovery, looking out into the vast unknown. The mysteries of gravity, dark matter, and dark energy are not just scientific puzzles, but philosophical challenges that force us to rethink our place in the universe. The answers to these questions may be more profound than we could ever have imagined. They could reshape our understanding of reality, revealing a cosmos far stranger and more complex than we ever thought possible. Perhaps in solving the mystery of these gravity wells, we will unlock the key to understanding the very fabric of the universe. And perhaps, as we uncover the truths that lie hidden beneath the surface, we will find that the universe is far more interconnected, more dynamic, and more mysterious than we ever dared to dream. The journey to uncover these truths may be long and difficult, but the potential rewards a deeper understanding of gravity, space, and the very structure of reality itself are worth the pursuit. As we continue on this journey, let us remain open to the possibility that the answers we seek are not just around the corner, but lie in the deepest, most uncharted realms of the cosmos, waiting to be discovered.